I have to introduce Martin Holler as the next speaker from the University of Graz. He's going to talk about analysis and applications of structural prior-based total variation regularization for inverse problems.
Thank you very much. So thank you for the patience and also thank you for still being here. So this talk is going to be about regularization for inverse problems using structural priors, and I will first try to give you a brief outline of what it means. So let me consider a particular example. So we assume that we have not only one measurement, but we have two measurements available which measure somehow related quantities. So a typical example would be we have an MR measurement, so this would be Fourier coefficients.
I think you're not wearing a microphone.
Okay. Is it better now? Okay. So we assume that we have two different measurements of the same quantity available, which are somehow related. So in this case, it would be an MR measurement and a PET measurement of, for instance, a head image. And we assume that one of the two forward operators is somehow better conditioned in the sense that it's easy to invert. So we invert, for instance, in this case, the MR image. We get a reconstructed image, which we assume that is somehow related also to the image that we have taken with the PET, and we want to use this information in order to reconstruct the PET image. And as you can see, like on the gray level scale, these images are very different, so we don't want to couple them in the gray value scale, but we would like to enforce some structural coupling. So the assumption is that somehow there are structures like the interfaces of different tissue types which are related. So we have this image somehow reconstructed, we hope that there are no artifacts anymore, and we want to use prior information from this image in order to reconstruct a more ill-conditioned image reconstruction problem. And with this, we would hope to transfer some of the features from this image to the other image, and with this, improve the reconstruction process. So the variational model that is underlying this procedure is as follows. So we assume we have given some V, and we want to minimize all possible images U, some data discrepancy, which relates here to the PET measurement, and some regularization prior, which now depends on the prior information V. And just as a side remark, as a second possibility, what we could do in this situation is that you do not regard one of the images to be superior than the other, but you treat them more on an equal level. So you could also do joint reconstruction in the sense that you want to couple them both at the reconstruction stage and use somehow shared information during the reconstruction in order to reconstruct both, and with that hope that you have a feature transfer in both directions so that you can aid the reconstructions of each of the modalities at the same time. And the underlying variational model would be then to minimize over both images simultaneously. So U would be the PET image and V the MR image, joint regularization, and two data discrepancies. And those two different approaches have their pros and cons. So the advantage of the first approach is that you are somehow more flexible because you have one of the images fixed, so you can have much more models which are still convex when you fix one of the images. So you can enforce quite a strong coupling. However, of course, you have information transfer only in one direction, and whatever mistake you make when you reconstruct this image, it will be fixed and potentially will be transferred to the other image. Here you have mutual information transfer, you have no fixed artifacts a priori, but of course you're a bit less flexible, in particular if you want to stay convex. So if you want to have a convex prior which jointly allows you to reconstruct the two images, it's a bit more restrictive than in this situation. And so both of these approaches have quite a few applications. So for instance, Simon Erich and Matthias Erhard had done a lot of work on this. I think both are interesting, and in this talk we would like to consider this first approach. So we assume that we have given a prior image and we want to use it in order to reconstruct the second one. And as I said, so there are a couple of papers, in particular recent papers, who consider this setting from the application point of view for multi-convex MR reconstruction or PET reconstruction or other topics. And in this work I would like to do a bit more on the analysis side of this type of priors. And I will not consider an arbitrary prior, but a restrictive prior, namely a structural GV type prior, which means that we have some integrand, which depends now on the prior image V, and we integrate, the integrand is spatially dependent, so it depends in space and also on the gradient of the image. So this would be the prior that we use for regularization, and this would be the data discrepancy. In particular cases that are covered by the settings are many. For instance, the easiest case would be weighted TV, so this J is just a spatially dependent weight times the norm of the gradient. So of course if the weight is just 1, this would be TV. So it can be spatially dependent, so it could for instance be 1 over the gradient of V. So you would have this means that you do not want to penalize the gradient of U if the gradient of V is very large, and you want to penalize it if it's very small. So you somehow want to couple the two gradients, and the regularization functional would look like this. A bit more and a bit more advanced version would be structural type TV or PLS, as introduced by Matthias Erhard. So that they would have some kind of matrix here, which is the projection on the orthogonal component to the gradient of the prior image. So you just penalize the orthogonal component of the gradient to this prior image. So anything which is aligned with the gradient of the prior will not be penalized, and everything which is not aligned will be penalized. And the corresponding regularization function will look like this. So these are two instances which are used in practical applications. And what I would like to consider in this talk is, as I said, more the analytical side. So those I've used in the discrete setting, but there are some issues if you want to consider this in the continuous setting. For instance, the gradient of u and the gradient of v are a priori only finite radon measures, because you typically would like to work with the BV space for images. So there are some questions regarding how to properly define this. What about existence of lower semi-continuity? What are the conditions on the integrand to get this? What do you need to have really a regularizing effect? So what regularization properties can you expect? And I will try to answer some of these questions during my talk. And it will be divided into 4 sections. So in the first section I will repeat the classical theory of functions of a measure, which allows you to give sense to this definition. Then I will consider a bit regularization and duality for this kind of problems. Then I will like to consider the application to inverse problems with Poisson noise in a bit more detail. And at the end I would like to show some practical realization for time-of-flight patch reconstruction. So let's first consider how to properly define this integrand. And as I said, there is a very big theory behind it, which is very classical and exists for a long time. So we use the following assumptions. So now we have this integrand J, for which I do no longer denote the dependence on V, but this will allow us to incorporate the prior information. And we have the following standard assumptions. So we want it to be convex and positively one-homogeneous in the second component. We want it to grow at most linearly in the limit, and we want it to be even in the second variable. So those are rather standard assumptions which are fulfilled by most of the TV type priors that you can imagine. And the strategy to then define a structural prior is as follows. So first you say, okay, I only consider images which are smooth enough. So I define it, sorry, this should be from LP to 0 infinity. I define it to be just what you want. So I just integrate the prior of the gradient if the function is sufficiently smooth, so that the gradient is really a function. So if u is in W11, I just integrate my gradient. If this is not the case, I just set it to infinity. Okay, so this isn't clear if this makes sense, but at least this is a useful definition, or this is a practical definition. But now, of course, this is not very satisfactory, because on the one hand, you would like to have a prior which is finite also for functions that do not allow a gradient which is a function again, and also there's a question of whether this is lower semi-continuous or not. And the classical approach, what you do is then you just consider the lower semi-continuous relaxation of this. So you consider all possible sequences which converge to your image u in the LP norm, and you take the lim-inf of the sequences, and then you take the largest lower bound of all these, which is the lower semi-continuous relaxation. So by definition, you know that this is lower semi-continuous. The question is, what does it look like, and can you use it for regularization? Okay, so this would be the prior we would be interested in. Now the question is, how can we compute it? And duality helps you in this respect. So since everything is convex, we can just compute the lower semi-continuous relaxation by biconjugation. So just to remember, so this is the convex conjugate of a function would be defined like this, and the biconjugate would be defined here. And then, since everything is convex, with the right topology, you know that the lower semi-continuous relaxation is the biconjugate. Okay, so just to recap, so we have a way of defining our integrand, but this is a priori not lower semi-continuous. So we take the lower semi-continuous relaxation. We can use this for regularization. However, the question is, how does it look like explicitly? What can we say about it? And to compute it, we can use convex conjugation. So we need first the convex conjugate, and then the second, the biconjugate of this function. For the first convex conjugate, there's a classical result by Bushitte and Dalmasa in 1991 and 93, I think, which says that under the assumptions we had, so under fairly weak assumption, you can compute the convex conjugate explicitly. It's just the indicator function of the set, whose definition involves the polar of your integrand. So, for instance, in the case of TV, you will all recognize this. This would just be the infinity norm. So you say that the infinity norm must be less or equal than 1. where here this is a definition of the polar, so this is just a pointwise quantity which you can compute in most of the cases, and this would just be the space of LP functions whose divergence is again an LP function. So in particular, for instance, if you consider weighted TV, so if your integrand is just a weight times the norm of your vector, then this set would just be a pointwise constraint on your dual variable, and you have it explicitly and you can project on it. And also if you consider the structural TV type prior, so you project on the orthogonal complement of the gradient of the prior image, should be a gradient here, then you can again compute it explicitly. You just have a infinity constraint and you have some orthogonality constraint in a dual variable. So without any additional assumptions, just using the assumptions J1 to J3, we can write down the convex conjugate, and it has a rather simple form, so it could be computed in applications. But as I said, we are interested in the biconjugate. We want to have the convex relaxation, the lower semi-continuous relaxation. So what can we say about the biconjugate? And there is a lot of work in this direction. So a series of works, which I think peaks in a work of Fusco in 2008, which considers the question of how can the biconjugate, how is it explicitly defined? And to obtain this, we need some additional assumptions. So first of all, we assume again that our integrand satisfies the three standard assumptions. And then there are some more general assumptions, but what I write here is then either we say the integrand must be essentially weighted TV with the weight having some spatial regularity, so it must be in BV, or it must be coercive, so we must have a uniform lower bound in the second variable, and again we must be in BV in the first variable. If one of these two conditions is satisfied, so either in both cases we need regularity in space of the integrand, and we need either a simple form or coercivity. But if one of those conditions is satisfied, then you can write down the biconjugate explicitly. You just use the decomposition of your measure, of this du measure, and you can write it down by using the approximate lower limit of the integrand J. So just maybe as a remark in particular, so if J is again weighted TV, the biconjugate is again weighted TV, just that you replace the weight here by the approximate lower limit. Okay, so what does it mean? Again, we can also get the biconjugate explicitly, but only under some additional assumptions. Either we need regularity in space of the prior, or we need coercivity. And this is a bit disappointing, because for instance, when we consider the structural TV type priors, they do not satisfy this. So if you would define this somehow from a function in PV, from the gradient of a function in PV, then we would not have regularity in space, and if we take the projection on the orthogonal component, we would also not have this coercivity constraint. Okay, so the question is, can we somehow overcome this? But what we can remember is we have the definition of the function, we have explicitly the convex conjugate in all situations, but we do not have the explicit representation of the biconjugate. And the goal of the second section would be to somehow overcome this by using duality results. So what we're interested in now is we want to solve this linear inverse problems. So we want to infirmize over all functions in LP the relaxation of our regularization term plus some, in this case, a discrepancy term. But we have to keep in mind that we do not know this term explicitly, at least without any additional assumptions. So we would like to find some approach to solve this problem without knowing the term explicitly. And one approach would be to just look at the pre-dual problem. So you can, because in the pre-dual now you just have R star appearing, so the conjugate, which is the indicator function. So this would be fine. We would just need the indicator function and we would just need to project on the set. However, this would involve the convex conjugate of our data term, which is again not given explicitly unless in some simple situations when the K is the identity or K star K is invertible. So this is also not a very good solution to this problem, because as I said, this quantity is not given explicitly. But you can do something in between, so you can consider a saddle point reformulation of this problem. So you can dualize the regularization term, but not dualize the data discrepancy term. So this would be a reformulation of the original problem, which does not involve any quantity that we do not know. It just has the primal of the data term and the pre-dual of the regularization term. So all of these quantities are known in the general situation and we can be computed. But the question is, when can we show that these two problems are really equivalent? But this would be the idea. So the idea would be just, instead of solving this problem, which involves R double star that we do not know, we just solve the saddle point problem. And we hope or want to show that by solving the saddle point problem, we get a solution to the original problem. And the question is, what are the additional conditions in order for this to hold? And we would also do this in a more general setting, so instead of considering a norm discrepancy, because we're interested in the application to PET, we would just also like to do this with a more general data fidelity term and essentially obtain the same result. Okay, so under what conditions can we do this? Well, there's one thing, so if we really obtain equivalence, it would in particular mean that we have existence of a solution here and existence of a solution there, and in this respect there's a negative result, so that tells us without any additional assumptions we cannot even expect existence of a solution. So if you just consider the simple case of weighted TV, and we have a weight which is smooth, it's zero only in one point, but it's not uniformly bounded away from zero. Then you can quite easily construct a counterexample where the original primal problem does not admit a solution. So the idea is the following. So you assume that your weight function converges to zero on these circles, so it's less than 1 over squared on each of the circles, and the circles become smaller and smaller. So essentially, if you have jumps on these circles, they are going to be penalized less and less. Then you take a forward operator just to be the embedding of L2 in the space of distributions, so the dual of the C1 functions, and as data you just take the delta peak at zero, so in the center of these circles, and then you can just construct an infimizing sequence, which is the characteristic function of these disks, which are multiplied by an appropriate constant such that it blows up. And you take this smaller and smaller, and you see that the jump will always be on the circles, so it will become, and it will be penalized by a weight which is less than 1 over squared, and if you choose the weights right, you can see that both the regularization term converges to zero, but you also approximate the delta peak. So both the regularization and the data fidelity term will go to zero. So you can show that the infimum of this is zero, however the minimum, this cannot be achieved because the delta distribution is not a regular function. So this is somehow a negative result, so it tells us that we cannot even expect existence of the primal problem without any additional assumptions on the integrand J. So let's look in more detail what are the assumptions. And there are two situations that we can consider. Either we say either the integrand is uniformly bounded away from zero, which is also what we had before in the result of Fusco, where we had this explicit characterization, or we assume that the forward operator has closed range and finite dimensional kernel. And I will comment on this in a second. But if either of the two assumptions is satisfied, then one can show that there exists a solution to the primal problem. Also that there are a solution to the corresponding dual problem and to the saddle point problem, and all of the problems are equivalent in the sense that if I solve the saddle point problem, I also solve the primal problem. So this means under one of these two assumptions, I can try to solve the saddle point problem, which does not require explicit knowledge of this A double star, and I obtain a solution of the original problem, which involves the lower semi-continuous relaxation of my regularizer. Now let's look again a bit more closer on the conditions that we have. So we say that either we need coercivity. Okay, this is a bit disappointing, but apparently this is what's necessary, because we have seen before without coercivity we cannot even expect existence of a solution. Or we have this condition of our forward operator, which essentially says that the ill-posed problem is well-posed. So essentially we have the identity. So the result tells us that if we want to use structural prior regularization in inverse problems, either the prior needs to be uniformly bounded away from zero, or we should have a well-posed problem in the sense that the range is closed so that the forward operator is essentially continuously invertible. Okay, and this result can also be obtained in a slightly more general setting. So now we assume that we have just some data discrepancy. We pose some assumptions, so it needs to be convex, continuous and finite at zero, and coercive. And again, we have the same result. So if either the integrand is coercive or the range of our operator is closed and the kernel is finite dimensional, then we again get existence of a solution to the primal problem, to a corresponding dual problem, and we get equivalence to the saddle point problem. Okay, so just a quick note on how the proof works. So maybe first let's look again what we need. So these two, what we need on the integrand. So we need that it's convex, continuous, and finite at zero, and it needs to be coercive. So if you consider this, in the previous case, this was just a norm, so this is all satisfied. coercivity you would expect. It's a bit surprising that you also need continuity 0, but this comes out from the proof somehow. So if you look at the proof, for showing equivalence of the primal and the dual problem, the settlement problem, there are two ingredients that you need to show. You need to show the conditions for strict duality, and you need to show existence of the dual problem. So for showing strict duality, there is this result per touche and précise, which is very useful, which says that strict duality holds whenever this condition is satisfied. So I take the union of all positive numbers, k star of the domain of my data discrepancy term, minus the divergence of C, where C is not a constraint set, which is defined by the regularizer, by the integrand. And if you look at this condition, you can already see how these two assumptions somehow pop out, because either I assume that J is uniformly bounded away from 0, which means that the C has somehow a small ball around 0 contained inside. So if I blow it up with this with the positive numbers, I get essentially all the space except for the constant functions. So this is how one condition arises. Whereas if I do not have this, if I do not know anything about C, I need to get this closed vector space condition somehow from the other part. And there I need, and here if I assume that D is coercive, it means that D star is continuous at 0. So again, the domain here will contain some epsilon ball around 0, which means that this will give me all of the range of K star essentially, which is a closed vector space if and only if the range of K is closed. Okay, so this is why we need the two conditions. So either we need somehow to get a closed vector space here, and either we get it from the regularizer by using this set, or we get it from the forward operator by using this set. This shows strict duality. And so far we have not needed continuity as 0. But the second thing that we need to show is existence for the pre-dual, and this is where the continuity of 0 hits in. Because the pre-dual here, for the pre-dual, we have to minimize a quantity which depends now on the dual of the concatenation of the data discrepancy and the operator. And we know that this is coercive if and only if the original functional is continuous at 0. So continuity at 0, which is trivially satisfied for the norm, gives us coercivity of this term in the pre-dual problem, and hence existence of a solution. So just to get existence, we would not need, of the primal problem, we would not need this continuity, but in order to get equivalence to the saddle point reformulation, we also need that our data discrepancy is continuous at 0, which again is trivially satisfied for the norm. Okay. So now let's look at some applications. So we have seen before the application to any inverse problem where you have a norm discrepancy and the linear operator is trivial. So we would like to look at the applications to inverse problems with the Poisson noise. And this is motivated by PET imaging. So let me just give you a short introduction to PET imaging. So what happens in PET imaging? Well, in PET you have some radioactive tracer which is injected into the body. And what you measure is the decay of this tracer essentially. So you inject the tracer into the person, you wait some time, the tracer accumulates, and then it decays, and due to this decay it emits some photons. So the person would be here inside, and you have rings of detectors around the person. And so there are typically, so the decay of this radioactive tracer causes two photons to be emitted approximately in opposite direction. So they hit two detector sections in almost opposite direction. And whenever this happens, the PET machine records a coincidence event, so to say. So it records that along this line there must have been a decay. So you can see that essentially what you measure is the radon transform, because for each line connecting two possible detectors, you somehow have information of how much decay has happened on this line. So the principle is rather simple. However, in practical applications there are many issues, such as scatter, random, and attenuation correction. So for instance, there will always be a certain amount of random events which happen during the measurement, which causes some random measurements that you cannot connect to anything which really happened. So for this reason you have the following forward model. So you have your image U, which is the unknown. Then you have a forward operator, which is essentially the radon transform. You have an attenuation map that you estimate that a priori is unknown, but you estimate it from the data. And you have a term which is for the scatter and random correction, which is again a priori unknown, but as I said, typically assume these two to be given because the PET machine gives you a rough estimate of these two quantities. So the forward model would just be that you have a linear forward mapping, and an additive contamination term which comes from the scatter and random events. And since you essentially count photons during the measurement, you assume that the noise is Poisson distributed. And this is why I use the Kullback-Leibler divergence for data discrepancy. Okay, so now coming back to our problem, what we consider now is our regularization function R double star, which is the lower semi-continuous relaxation of some structural prior that we have defined. And the data discrepancy will be a Kullback-Leibler divergence plus a positivity constraint on the image. And we use the following basic assumptions. So this is now the more general setting. So we have just a linear operator from LP to L1. We use that it's positive whenever U is positive. This is satisfied by the Radon transform because you integrate the unknown quantity over lines. We also assume that the constant functions are contained in the range of K star, which is also a rather weak assumption. We have some boundedness assumption of our domain, and we assume, of course, that the measurements are positive, and in particular, this contamination measurement is strictly positive, so it can never be zero. However, it might be important to note that we do not assume that it's uniformly bounded away from zero. So this is also something which is quite often assumed. However, you have to take into account that this corresponds to some measurements of lines. So if you look at the Radon transform, maybe you can show this. So if you have the Radon transform, so you have your image, which is somehow contained in a disk that you want to measure, and you take line integrals, which corresponds to the integration of the image on the line. So typically your object will be bounded away from the boundary, so the measurement will be zero or almost zero if you are outside of the object of interest. However, you still have some scatter effects which come from random events. But when the lines approximate the boundary in the continuous model, of course the measurement will go to zero because the lines will become shorter and shorter. So so to say the random events that you measure on these lines will become zero. So this is why it's maybe not so reasonable to assume that they're uniformly bounded away from zero. However, it is reasonable to assume that they are strictly positive. And we have some additional integrability assumptions, which are also, I think, not too strict and should be satisfied in a reasonable model for this situation. Okay, so with these assumptions, we would like to apply now our framework that we had before. So we want to show that since we do not know in general how this term explicitly looks like, we would like to show equivalence to the Seidelman problem, and we would like to solve the Seidelman problem. And the main requirements that we had was, if you remember, on the data term was coercivity and continuity at zero. And in order to obtain this, we have to work a bit on our data term, because a priori this will not be continuous at zero and also not coercive, because this quantity blows up as the measurement goes to zero. And in order to compensate for that, we use a small modification. So we first consider just the Kullback-Leibler divergence from the PET measurement, and we define the following integrand. So if a variable is positive, we just take the one from the Kullback-Leibler divergence. However, if it's negative, we just extrapolate linearly. So we do not take the original one, we just modify it with a linear term. And then we define our data term using this integrand, plus an additional L1 penalization of the negative part of the measurement. Now, why does this make sense? So this is done, of course, for technical reasons, because we want our assumptions to be satisfied, but it is also, in fact, does not modify the original problem, because we only modify our problem for negative measurements. But if you remember, we had this positivity constraint anyway, so the image will be always positive, hence the forward mapping of the image will also be positive. So in fact, we do not modify the problem, we just define the data term differently, but the result will be exactly the same. So this is not a real modification, it's just a small trick in order to deal with the problems around zero, and this can be done because you have that the C0 is always strictly larger than zero. So we exploit this fact in order to modify our data term close around zero without changing the original solution. And then using this slightly modified data term, which I said again is not a real modification because it does not change the solution, we can show that this is convex, continuous in L1, and it's also coercive in the L1 topology, so it satisfies everything that we need. The second thing we have to deal with is the infinity constraint, the positivity constraint, as this obviously is not continuous in an LP topology. And here we have to do a real modification of our problem. Instead of considering the positivity constraint, we do something like an exact penalization. So we take just the negative part of our image, penalize it with an L1 norm and an arbitrary high constant. And as you will see later on, there are reasons why one would believe that this has the same effect as the positivity constraint. So this is known, so this type of L1 penalization is known as exact penalization. In some situations you can show that for reasonably large m this has exactly the same effect. We cannot show this in our setting, but at least numerically we would expect this, as you will see later. Okay, and using these two modifications, where this one is the only one that really affects the problem, we now consider the modified problem for patch reconstruction. And we can, again, we know now that as long as the integrand is bounded away from 0, our results apply. So we get existence of the solution. We also get existence of the saddle point problem and equivalence of the two. So we can solve the saddle point problem and obtain obtain a solution of the original problem with the unknown lower semi-continuous relaxation of the regularization term. Okay, so as last, let me now show how this can be realized in practice for patch reconstruction. So now we assume that we have some MR image given. We have an MR prior image given, and we assume that the gradient of this image is an L1 log. Okay, so this is the regularity we need in order for this to make sense. And then we want to define a prior for the patch reconstruction that incorporates this information of the MR gradient. And what we do is the following. So we use two parameters. So we define W basically to be the direction of the gradient by using some parameter for regularized division to avoid problems when it's 0. And then we define our matrix as the identity minus the tensor product of this vector times a factor eta, which is smaller than 1. And you will see why we do this soon. So then we define the integrand by using this matrix, and we can see the following effect. So first of all, it's clear that this integrand satisfies J1 to J3. Then you can see what's the effect of the integrand, namely just a small change of variables shows you that basically you penalize the norm of Z, so the norm of the gradient, minus this quantity, which involves an inner product of this term W with the normalization of Z. And this is the directional dependent prior. So as long as, so this will be 0 if the two priors are aligned, or it will be very small at least if the two gradients are aligned, and it will become larger if they are the more they differ from each other, so to say. And if this parameter eta would be 1, it would be really 0 whenever the gradient of, whenever this quantity is aligned with the prior gradient W. However, we cannot allow for this because then we would not have any regularization effect. So we pick the eta slightly smaller than 1. And we also obtain this coercivity estimate. So this prior is then really large or equal than the square root of 1 minus eta squared times Z. So we have the coercivity estimate, and the assumptions that we had before are satisfied. Hence we can apply our result, and we know with this kind of prior and the data fidelity for the patch reconstruction problem, we get well-postness and equivalence to a saddle point reformulation. Okay, so this would be about the continuous setting. Now just a quick note, how can we realize this in practice? So this is now after discretization, we have to solve this saddle point problem, where now I have just introduced a small change of variables in order to avoid a difficult projection on the prior set. So we have, after discretization, we have to solve the saddle point problem. I have done a slightly additional smoothing of the data term in order to get the derivative of it to be Lipschitz continuous. And then we can employ an extension of the primal dual algorithm, which is just, we take essentially the classical primal dual algorithm by Jean-Paul Pock, and we take an explicit gradient descent step with respect to the data fidelity term. So, and for this algorithm, convergence can be guaranteed as long as you have reasonably small step sizes. And the point is now, so all operations are of course explicit. You just have to compute your forward mapping of the inverse problem, and you have this prox mapping, which corresponds to the regularized positivity constraint. And this is not a point that I mentioned before. So if you look at this prox mapping, this is a soft thresholding, and it means that every value, so essentially if you have, if you look at your image, it means that every value between 0 and minus sigma m will be thresholded to 0. And only those values which are below minus sigma m will remain negative. So as long as the m is large enough, this will always have the same effect as a projection to the positive values somehow. And this projection is just a standard prox for the L2 norm. Okay, so at last I would like to show some numerical results, which are in fact from a previous paper where we use a slightly different algorithm, but the same prior technique. So this would be a phantom results where we have a PET image and an MR image, which would be the ground truth. And we compare a standard method for PET reconstruction, which would be EM iterations with the structural prior, and you can see that the prior really has a very strong effect, so it really aids a lot in the computation, in the improvement of the reconstruction. So these are different reconstructions for different weights of the prior. So the higher, the more regularization you employ, and you can see that you can really improve a lot on the resolution here. And we have also done some quantitative evaluation, and you can see that because PET is quantitative, and you can see that the quantitative values of the reconstruction are also much more improved compared to the standard reconstruction. And you can also apply this to real patient data. So this was a study which we did with 3D time of flight PET data. And again, we compare the standard method, which is maximum likelihood EM, to this prior-based regularization, and also a second different prior, which does not come from a variational model. And again, you see that you obtain a much sharper reconstruction here in the situation. Okay, so this concludes my talk. So again, to repeat, we have considered structural priors, structural prior-based regularization. The main message is that there is a classical framework how to define this. You can also, when you define it, the quantity that you want to use for computation is the convex relaxation. This is not available explicitly without additional requirements. However, using this trick with the saddle point formulation, you can, at least without requiring additional spatial regularity, you can solve the relaxed problem without even knowing the relaxation of the prior. And you obtain well-postness in a general setting, and duality results under reasonable conditions. Okay, and with this, just like to give some references. So this would be the paper which has been recently submitted, where we discussed this method, and some other papers for reference. Thank you for your attention.
So we have questions. No questions?
Yes.
So like without these extra assumptions, so you can show that there doesn't exist a solution in what was LP or L2.
The forward operator was mapping from LP to the space of distributions, more or less.
So I mean, another option would be maybe to look at a different function space where the solution could lie in.
Yes, probably, but I think in general it will be difficult. I think it's hard. I would not expect existence of a solution if you do not have this coercivity. I mean, yeah. So
what kind of norm are you using to measure the distance? Because you are measuring distance of a function to a distribution, basically. Or
yes, I'm measuring the induced dual norm. So I take the dual of the C1 functions, of the convective support of C1 functions, and I take the distance in the dual norm. So taking
isn't that basically like it would always stay as 2 or something? You don't get convergence of a function to a distribution. Unless you some very, very specific.
No, I think it was because you also have the first. I think because you also include the first derivative, so it's not just the continuous functions. So it's not the difference in the radon measure, but you have really the dual of the C1 functions, which gives you a slightly different norm, and there you have convergence, if I remember correctly. So I think this was the reason why we did not use the dual of the continuous function, but dual of the C1 functions. But maybe we can discuss it often.
Yeah.
So another question. So in your numerical experiments, if I remember correctly from a previous talk, that you used the version sort of like where the smoothing parameters are 0, such that you actually are in the case where you may not have a solution. Do you observe any numerical instabilities or something? So that it numerically works fine?
Yes, so numerical. Yes, so I did not observe anything which I would relate to this issue. I mean, of course, you always have feature transfer, for instance, which could be somehow caused by this, because if you allow the integrand to be 0, you can have things without any cost. So this might allow you to introduce features which might not be introduced if you have at least a small cost. But of course, it's always the question. I mean, if you have a very small parameter, it will numerically have the same effect than choosing the parameter to be 0. So and the experiments are showed here, and you're right. So we just chose the parameters, to be 0 because this was a paper which I did previously before this work. In this work we also have some numerical examples where we now use the parameter which is a bit away from 0.
Right, so you didn't observe any point artifacts that would be kind of like related to your example where you showed the solution doesn't exist, that something converges to a Dirac or something?
No, we did not observe this, no.
Okay, because like in a related work, I mean, I have observed this in practice that sometimes, I mean, if you choose a parameter that's too small, you actually observe point artifacts. There would be something like a numerical verification a bit of your
this could be. I mean, the original question I was asking is whether you can show this has a regularization effect, so that you can show that if you perturb the data a bit, then the solution perturbs a bit. But the prerequisite for this is, of course, existence of a solution. So, and we saw that this fails. And if you have this boundedness away from 0, you're essentially equivalent to TV. So you have all the standard results regarding regularization. You have stability and so on.
In a lot of situations, maybe in the future, you might have multiple structural overlaps. So, for example, structural similarity over time or structural similarity over scales, if you think about deep learning. I think several other situations like that. What do you think is the limitation in your current theory or in the numerics that we have to overcome to treat multiple?
I think there are different, so as I said at the very beginning, there are two different approaches. So one is that you say, okay, I have a fixed one ground truth and I use this as structural prior for different reconstructions. So in this case, if I would have multi-spectral data, I would just do the same for all the different spectra. So I think there would be, so this would be like a direct generalization of this. The other one would be this joint reconstruction where you treat all of them equally. And we have a recent paper which will be submitted soon, actually, where we consider the theory of this, so how to choose parameters and what is the regularization effect of this. I think this can be generalized easily. So you can use, for instance, a nuclear norm or Frobenius norm coupling over multiple contrasts. Then you have multiple data fidelities, and this easily generalizes to multiple contrasts.
When you say structural prior, you primarily think of edges of singularities, right?
Yeah.
So, in some sense, there is also, with the wavefront set, you can essentially also see how singularities are transformed. You can actually read them off in data.
Pardon again?
When you look at the wavefront set formulation of singularities, you can also account for how they transform. So you can essentially read off the singularities or from the data. So we're just figuring, since you're doing joint reconstruction.
No, in this setting we do not joint. You fix one and reconstruct.
I know. But okay, let me rephrase. If you would do joint reconstruction, do you think it's it's a vague, very open-ended question now? It's not even a precisely formulated one. Do you think it would be possible to somehow account for how the singularities are transformed by the forward operator, and not just look at the reconstructed side and just try to find similarities?
Well, I think this would definitely be interesting. Yeah, I mean, you could always. The question is if you can do it on such a small scale. I mean, if you have, for instance, particular directions, it relates a bit to the talk of Ichudong. If you have some particular directions, this you can maybe infer from your data, and then you can use this as a prior information. The exact localization of your edge sets, I think, would be difficult. But in principle, I think this would be an approach for joint reconstruction, that you estimate some kind of prior from your data.
If there are no further questions, I would say let's thank Martin again.